The idea of a limit is to figure out what happens to values as they approach another value. And more often than not in calculus, those values are going to be related to the slope. But in this case, for an example, I have just picked a regular function. But let me read over the limit notation value first. So here, this limit notation reads, the limit of f of x, which is a function, as x approaches a, is equal to some value. And again, with limits, it's not important what happens at a. I'm only looking for what happens when I get very, very close to a. So I picked an example where a is an undefined answer, cannot have a as a point here. There's a hole in this graph because it'll be undefined. But I'm not interested in what happens at a, I'm only interested in what appears to be happening before I get to a, or 1 in this case. So I set up two tables. I approached it with values from the left-hand side of 1, and then I approached it with values from the right-hand side of 1. So here I'm half a unit away. That gives me some function value, a tenth, a hundredth, a thousandth, a 10,000th. And these values get closer and closer and closer to 0.5. And on the right-hand side as well, I did the exact same thing, half a unit, tenth, hundredth, thousandth, 10,000th. These values also appear to approach 0.5. So the limit appears, for this function anyways, to be 1/2. And this is basically how limits work. I look at my point that I'm trying to find the limit of, and then I approach it from the left-hand side. This is just using the numerical method. There are a lot of different ways to do it. You can look at graphs. There are a few ways of doing it. So I approach it from the left-hand side, and then I approach it from the right-hand side. And if those two numbers agree, then there is a limit there. Now, sometimes these number methods don't always work. Something like a sine or a cosine function, sometimes I'll get cases where unless I pick numbers that are, instead of 0.5, I might pick 0.5, and then instead of 0.9, I'll pick 0.8. Instead of 0.99, I might pick 0.93. So what that does is that it kind of thwarts the repeating answers that often happen in cyclic functions. Because whenever I go around in a circle, often what happens is I end up getting the same answer. So sometimes something might appear to be approaching some limit value, but it really isn't. And then if I were to look at it on a graph, then it would be more obvious that it is not in fact a limit. But that's not really the whole point of this. The whole point of this is just to really get a basic idea of what is trying to be achieved by taking a limit, and that's just to see where numbers generally tend to be going. And there's a couple more things to do with notation here, and that is the minus and plus sign here. And all of this minus and plus sign means is that I'm approaching this number from the left side, and I'm approaching this number from the right side. Left side, right side. And I finally would just like to look at a couple of graphs just to get a better sense, again, of limits. And these, I'm only going to be looking for the limits of the function values. I'm not going to try to get fancy with slope values or anything like that right now. So here is an example where if I were to take the limit as this function approaches a, it's pretty obvious that it's going to be a. I mean, there are no holes in it or anything like that. I mean, if it's just a regular function, just like, let's just say it wasn't really curvy, it's just y is equal to x, and I want to know what happened when x goes to 1. Well, it would appear that it would go to 1. I could pick 0.9, 0.99, 0.99, and since it's just 1 to 1, just whatever x is, y is equal to that. It's just a really simple example. If I were to put 1 in there, I'll get 1. So the limit appears to go to 1. So when there's a continuous function like this, it's pretty straightforward. Now here is an example where it is a continued, well, it's a function that doesn't have any holes in it, but there is no limit. So when I approach the value a from the left side, the function values are going to appear to go to whatever number is right here. When I approach the values from the right, it's going to appear to be this number right here. So the left and the right sides don't add up, and if they're not the same, then there is no limit. So here's an example similar to the one that's done above, where there's a function but there's a hole in it. But because with limits, it's not really what's not important is what actually happens at a. If I'm looking here, the values still appear to go to whatever this value is right here. So my limit will be whatever that value is. The left and right sides will agree to this, and therefore there will be a limit of whatever this number is right here, even though there's a hole there. And that's what happened with this example up here. For 1, there is no value, but the limit of that is still 1/2. The function values still appear to go to 1/2. And here's one more example, and it's similar to the last one, where I've got a hole right here, but I do actually have a value for a, but it's just down here instead. Well, the limit would still be whatever this number is up here, and not this one down here. This is completely irrelevant. For limits, again, it is not important what is happening at a. It's all about being superficial and just reading a book by its cover and just saying, well, it looks like that, so that is the limit. That's what limits are like, just looking at what appears to be happening.